Welcome to Senior Design Team 2211's video presentation on contactless underwater discharging and recharging of a vehicle battery. This video will cover the project overview, specifications and constraints, background knowledge, design, approach, and testing. Current industry practice requires surfacing an unmanned underwater vehicle before charging or discharging the battery system. The goal is to develop a bidirectional wireless charging system through inductive coupling. Communication between two microcontrollers will facilitate the charging direction and relay charging data. The project specifications are as follows. Bidirectional wireless transfer of 100-200 watts. Transfer of a distance of ½ inch. Communication between base station and UV. Transfer must work properly in both freshwater and saltwater. Must not cause interference with other systems in the UV. The project is based off of the properties of electromagnetic induction. Current flows in receiving coil when alternating current in transmitting coil produces varying magnetic field across the coupled coils. Our basic design follows this system block diagram. The user interface will allow switching between 3 modes of operation as well as indicators for charge state of supply and UV batteries. Modes will include UV charging, supply charging, no charging. Charging and discharging will be controlled by user input and facilitated through a buck converter. This will include a MOSFET driver that will adjust to the voltage and current entering the battery through the use of a PWM signal. Charger circuit will be in either constant current or constant voltage mode. Initially, the output of the charger will be kept at a constant current until a specified voltage is reached, at which point it will switch to a constant voltage mode. Full charge detected when the charging current reaches a specified value in constant voltage mode. When detected, the battery side microcontroller stops charging and tells the power supply microcontroller to stop sending data. The current and voltage of the charging system will be adjusted by the duty cycle of the PWM signal sent to the MOSFET driver. The duty cycle will be determined through a closed feedback loop which will gather the current and voltage values through a pair of sensors hooked up to the microcontroller ADCs. These sensors will also be used as safety measures by triggering a fail-safe to turn off charging if either the current or voltage pass safe levels. Our battery will be composed of individual lithium-ion cells, allowing for us to connect multiple cells in series and parallel to reach our desired voltage and current levels. Load testing will allow us to determine the exact battery level that we require, and we can add and remove cells to meet the voltage and current requirements. A symmetrical system using 2 coils will be pursued with dual full H-bridge setups. For parts, the 760,308,101,311 WPT transmitter coil was selected. It is capable of 400 W power transfer at 20 VDC. And exceeds paper power requirement, as to compensate for the decreased efficiency of saltwater and coil distance. It is constructed with Litz wire. The FG20X7S1H106KT06 ceramic capacitor is used to adjust the resonant frequency of the coil to around 20 kHz. The STM32L552 series microcontroller was selected to be the brain of the system. It features a 110 MHz clock frequency, the ability to control the H-bridge and battery charger through PWM generation, and the ability to measure voltage and current entering the batteries through the use of external sensors circuits and built-in ADCs. Communication between microcontrollers will be accomplished through serial AUX connection. 6 EPC9003C development boards were bought after given Cree board half-bridge evaluation board for testing. 2 boards will be combined to make the requisite H-bridge. An additional board will be used as the buck converter for the battery. Initial testing. A Cree evaluation board was used to make a half-bridge converter in order to understand the DC-AC conversion aspect of our system. 2 270 NF high-voltage capacitors were used with a VDC of 12 V. The PWM signals for the switching were sent from a 2-channel function generator. With coils stacked on top of each other, a 25 power resistor was used as the load for the receiving coil. A diode rectifier was added in between the coil and load so that data can be gathered. The voltage across the input and output were taken for a measure of efficiency, after varying the frequency and duty cycle. Currently optimizing the transfer frequency for underwater use. The coils are sealed in containers with around a 1 cm water gap. Test big design and construction. The coils are sealed inside of a PVC pipe fitting. The coil housing is able to slide along the rails of the test bed in order to test different water gaps. EPC board testing. Using the 1 PWM mode on the EPC board, several dry tests were conducted in the half-bridge configuration. Channel 3 is coil voltage, channel 4 is measured supply current. At 3.65 input 1A is pulled from DC supply. Using the 1 PWM mode on the EPC board, several dry tests were conducted in the full bridge configuration. Channel 3 is coil voltage, channel 4 is measured supply current. At 2.10 input 2A are pulled from DC supply. At this moment, the excessive current draw is inhibiting the scaling of transferred power. This flowchart represents the constant voltage mode system operation. This flowchart represents the constant current mode system operation. Thank you for your time. Sincerely, ECE Senior Design Team 2211.